Okay, we
Oh,
can.
there we go.
Yes, thank you.
Okay. So today I'm going to give you guys a short crash course in design of perturbation maps. And I want to teach you about 3 of my upcoming results that you can apply to your research today, and also introduce you to O-LOMAP, which stands for Optimal LOMAP, and that's my upcoming software package. And this talk was set up very well by Cenk, in the sense that we cover some similar topics. So first, I want to consider a case where we have 5 ligands and you want to think about all possible designs. And just to give you a sense of how the number of designs that you would have to calculate scales, for that simple problem, you would already have to have the number of designs that fit within this Skittle package here. It's 54 ounces. If, on the other hand, we had 8 ligands, and you just wanted to run 8 transformations, you would already have to fill a standard cubicle full of Skittles for the number of designs that your software has to sort between. If I added just 3 more edges to that, this room that I'm currently in would actually be filled. So do the current methods that you use, are they able to handle that problem? And that's the thing that O-LOMAP's really trying to tackle. So the first thing that we do is import a generalized similarity metric. The default is the LOMAP similarity scores, and that's based on what transformations are likely to perform well for relative binding free energy calculations. And then we use unsupervised machine learning to perform clustering, and that's to address the question of which nodes should be coupled together in a design. And we output a heat map for you, like the example shown here. And we form clusters of groups. For example, in this case, we would have 3 clusters, cluster 0, 1, and 2. And then those clusters can be sent on for optimization. But what exactly do I mean by optimal designs? That is a word that can be overused. And what I mean specifically is that the designs are statistically optimal. And so we'll use mathematical tools in the software. And what that means is that the language of O-LOMAP is linear algebra. And what you see here on the screen could potentially be intimidating, but it's actually something that most of us are very familiar with, which is a perturbation map. So let me show you how that transformation works. In each row where you see a -1 and a 1, that is in fact just an edge or a potential alchemical transformation. And each column is just a node or a ligand. So I'll call the number of nodes N and the number of edges K. And then this matrix, which is the design matrix, can just be embedded into this simple perturbation map. These objects are in fact the same thing. I can simplify the problem farther by embedding this graph into just a single variable, which I'll call A. And then there's an additional component, which is bringing back those similarity scores. And so that's the weights of the edges. And I'll call those weights, the collection of them, W. So the default for O-LOMAP is the LOMAP similarity scores, and that contains some rules, some of which are that we minimize atomic insertions and deletions, we preserve rings and net charge, and then we also avoid breaking rings and only break them if they're planar. And these 2 variables, A and W, come together in this equation that I'm showing you here. And that's simply your covariance matrix. So the only thing you have to understand about the covariance matrix C is that it's the collection of the predicted variances and covariances for the changes in free energy that we would like to estimate, the true changes in free energy. And so with that idea in mind, we can use C to actually tune the design by trying to iteratively find the design that gives us the lowest variances or the most information about the changes in free energy. This process is what we call optimization to form these optimal maps. The two main ones that we focus on in O-LOMAP are called A-optimal and D-optimal. These are just two different ways of minimizing the total variance and covariance. And for more details, I have an upcoming preprint that should be out soon. There's also more information in Yang and Huafang's 2019 and 2020, I think I switched the years here, publications. So now on to the main results that I want you guys to walk away with and that you can apply to your research in general. The first one is about the number of edges in these designs. And so I wanted to ask the question, how many edges should these designs have? And this ended up being very important for making O-LOMAP scalable and so that it didn't break for particular edge cases. So for this first thought experiment, we can consider the case of 4 ligands and the full design where we have all possible edges. And then I'll generate random graphs that have a fewer number of edges and measure the distance between the covariance matrices of both of these graphs. I'll continuously increase the number of edges and measure the distances. And I did this analysis for graphs that have 10, 20, and 40 ligands. And what you see is that you rapidly converge to the covariance matrix of the full design, both in terms of the distance and the error. And this black dot that you see in all 3 graphs, that's the point where the number of edges k is equal to n natural log n. Now this analysis here can seem somewhat overly theoretical, so I wanted to run simulations of how these graphs are likely to perform in terms of error. And so to do that, I ran many different combinations of nodes and edges. Each dot that you see on the plots here represent 200 replicates for each combination of edge number and node count. And each curve is for a constant number of nodes. And so if you read along the diagonal, you have an increase in the nodes. As you read along the x-axis, the edges are increasing. And for these low edge counts below 2n, you see that the mean squared error rapidly increases. This same data can be shown in this format, which is a little bit more digestible. And what you can see is that as designs get larger, if you were to just linearly increase the number of edges you have, you'll have a degradation in your results for large designs. So if you have a study where you invest a lot of money to say simulating for 100 different ligands, and you only had 100 edges, you'll get rather poor performance, and you could be throwing your money at the problem in a way that won't give you precise results. If, on the other hand, you simulated n natural log n number of edges, we find this stable precision point that stays constant as designs get larger. You could say that's a lot of edges to potentially simulate, but O-LOMAP has an additional tool within it, which is clustering, which actually helps you to save money on the total study of the ligands as you introduce clusters. So in the best case, you save the most money if you have very balanced clusters or the designs have the same number of ligands in them. And this is the cost saving. So if you introduce just 2 clusters, the cost of the total computational experiment drops dramatically. If, on the other hand, you have the most unbalanced clusters, you still save money. It's just at slightly increased cost. And so we provide this as a tool for you to do a cost and risk assessment of how precise you want your experiments to be before you run them and the total cost of doing the work. And then finally, O-LOMAP also reduces the total simulation time required. And this is based on a theoretical prediction just from information that's embedded within the designs. And so I measured the efficiencies of 5 different protein ligand benchmarking sets. And if you see a value of less than 1, it means that the optimal designs are more efficient than the reference, which are simple radial graphs and also low map graphs. And if you see a value greater than 1, it means that the optimal designs are less efficient or predicted to take longer to converge. And what we see consistently comparing D-optimal and A-optimal to radial and LOMAP is that we have a continuous improvement in the efficiencies. These are theoretical results. Michael, in his next talk, will show you some of his work during his internship on running simulations that actually bolster these results. So here's your cheat sheet from this crash course. First, as designs grow, add more edges or expect to lose precision, think the expected number of edges should be like n natural log n. You want to make designs smaller or use clustering for cost savings at this high precision count. And also optimal designs will reduce the total simulation time required. And then finally, the main takeaway that I want you to have from today is that these designs contain more information than just what transformations to run. And we can use that to predict precision a priori and cost, and also things like efficiency. If you scan the QR code here, it will send you to a working prototype of O-LOMAP. I'm currently working with Mulsey as a software fellow to improve the speed so that we can scale up to larger and larger designs. And with that, I'd like to thank Dr. David Mobley, who I've worked with as a postdoc for this past year on this project, funders and collaborators from Janssen, specifically Dr. David Hahn and Dr. Gary Tressedern, and then also my software mentors at Mulsey, Samuel Ellis and Levi Naden. And with that, I'd like to take any questions you have.
Thank you, Mary, for being even ahead of time. Thank you for this very exciting talk. Yes, so may I remind everyone that you can type in your questions in the Q&A box, and you can type in as many questions as you want because you will get answers even afterwards in writing. Yeah, so while we're waiting, so you're using this linear algebra approach. So have you tried to tie it up with machine learning as well to improve even better your results?
So the optimization process doesn't use machine learning, the clustering does, but so for example, the work that we were just shown, that's not necessarily incompatible. You could port in metrics that you learn through machine learning directly into O-LOMAP, but we haven't tried to use that for the optimization process, no.
Yeah, I think, I mean, of course, it's in starting right now, and it's very exciting. I think even if you keep advancing it, you could tie it up with other techniques as it goes on. It's definitely something very new and fresh. And I don't see any other questions here, but maybe people will write still in the chat. Someone says that we can't type in questions in the Q&A, have just messaged us. Yeah, it looks like there are some technical problems. So may I ask everyone, if you can't type in the Q&A box for some reason, can you send us
Zoe,
a message? Yes?
It's the panelist and the host who can't type in Q&A.
I see. Okay.
So everybody else should be able to do it. But if you are a host or a panelist, please just send it in the chat.
Right.
And as a moderator, we will pay attention to both Q&A and chat.
Okay. Or Xinkyung, if you have a question, you can just pick it up instead of writing it if you wanted to ask now.
Yes, you should be able to come off of mute, Shenshang.
Yes, sure. Thank you. Thanks for the great talk. I have a question about the optimization. It's a discrete optimization, right? So you try to add or remove an edge.
Mm-hmm.
And how well is how difficult it is? Like I assume there are many like local minimums, and is this done using a heuristic, like you make a random change and see if the score improves? Or it can always find the optimal?
So it's using the determinant and the trace of the covariance matrix. So that's the A-optimal and D-optimal. So I wouldn't describe it as a heuristic, more like a numerical quantification of the variance in the covariance matrix. And so what I use is the Fedora of Exchange. And I'm currently working on parallelizing the inner for loop of that process. But we calculate the different determinants and traces of the covariance matrices for all different possible exchanges. And if we find a better solution, we do the exchange and continue to iterate. There actually aren't that many local minima for these smaller designs, say like less than 50. So if I run multiple replicates, I often get the exact same design.
I see. Thank you.
Sure. And I actually have one potential request, which is that I put together a poll that I just put in the chat. Can people see that?
No, we'd have to type it in, I guess, to the Q&A for everyone.
Should I put it in?
But we can't. I don't know if there's a solution, Jonah, for Mary to share something with her attendees.
Jonah, I believe, is no longer on because
Okay.
he's teaching. But we have it here, Mary, so I'll talk to Hannah and I'll see if there's a way that we can post this for you.
Okay.
But do you want to finish your statement so at least people have an idea of when it comes, what it means?
Yes.
Yeah,
So
but
this,
also, sorry, Mary, I just tried the link and the link is, I don't have permission. The form can be viewed by users in the owner's organization only.
okay, I'll change the link and maybe email to you.
Thanks.
Are there any other questions?
Yeah, can you tell us more about the poll that the link that you're posting? What is it about?
Oh, yeah. So it's a poll for software questions so that I can work to improve basically the architecture so that more people will use it. So it's questions about how long the code can run and also what things are important for you and your projects.
All right. Well, thank you. You can post the link after you've changed the permissions in the chat, and we'll see how we will communicate it to the rest of the attendees. Thank you very much for a great talk. And with that, I would like to go on to our next speaker, who is the last before our poster session and break. So the next speaker is Michael Gilhofer from Janssen. Michael, you can share your screen.